Three-dimensional food printing begins with an idea that sounds almost futuristic, taking digital information and turning it into edible matter. A shape is first designed in software, that geometry is then sliced into machine-readable instructions, converted into toolpaths, and physically reconstructed layer by layer using food material as the building medium. In the simplest sense, this resembles additive manufacturing used in engineering. But in food systems, the challenge is much more complex because, unlike plastics or metals, food is not an inert material. It is a multi-component biological system whose flow, deformation, thermal behavior, and structural stability are governed by complex physico-chemical interactions. That is why three-dimensional food printing is not simply about making decorative shapes. It is a systems-level food engineering process in which digital design, material science, rheology, and post-processing must work together to create a stable, edible product.
At its heart, food printing is a process of controlled spatial organization. The printer does not simply place ingredients. It determines where material is deposited, how internal architecture is built, how layers interact, and how that arrangement affects final food quality. The internal geometry of a printed food can influence porosity, density, moisture migration, fracture behavior, heat transfer, nutrient localization, and ultimately texture perception during eating. In conventional food processing, many of these properties emerge indirectly from molding, baking, extrusion, or mixing. In food printing, they can be digitally designed as part of the fabrication process itself. This is one of the reasons why three-dimensional food printing has attracted interest for personalized nutrition, texture-modified foods for dysphagia patients, controlled nutrient delivery, and engineered sensory design.
But before any of that becomes possible, one scientific problem dominates everything else. Can the food material actually be printed? This is where rheology becomes central. Printable food formulations behave as engineered non-Newtonian systems. Their flow behavior changes depending on the mechanical forces applied to them. Unlike water, whose viscosity remains relatively constant, food inks are typically composed of proteins, starches, hydrocolloids, fats, fibers, sugars, dispersed particles, and water organized into structured multiphase systems. Their apparent viscosity, elasticity, yield behavior, and structural recovery are dynamic, not fixed, and these properties determine whether the material can survive the printing process. Consider extrusion-based food printing, the most widely used method. Inside the printing nozzle, the food ink is forced through a narrow channel under pressure. Under these conditions, the material must flow readily. To do this efficiently, it typically needs to exhibit shear thinning behavior, meaning its apparent viscosity decreases as shear rate increases. This allows the material to move through the nozzle without requiring excessive pressure, reducing clogging and promoting stable extrusion. Numerous rheological studies show that extrusion performance strongly depends on this balance between viscosity and shear thinning response. But as soon as the material leaves the nozzle, the engineering requirement changes completely. Now the ink must stop behaving like a fluid and begin behaving like a structure. The deposited strand must resist spreading. It must support its own weight. It must tolerate the load of subsequent layers. It must preserve dimensional fidelity. This is why printability is governed not by viscosity alone, but by a combination of rheological parameters including yield stress, viscoelasticity, structural recovery after shear, and the balance between elastic and viscous behavior, often described through parameters such as storage modulus, loss modulus, tan delta, and strain thinning behavior. Recent studies show that yield stress correlates strongly with printing force, while printing accuracy depends on more complex interactions involving yield behavior, viscoelastic recovery, and flow dynamics. In practical terms, a printable food ink must flow when pushed, but rebuild structure almost immediately after deposition. If viscosity is too low, the strand spreads and collapses. If viscosity is too high, extrusion becomes unstable. If yield stress is insufficient, layers flatten. If structural recovery is poor, vertical stacking fails. If elasticity dominates excessively, the material may fracture during extrusion instead of forming a continuous filament. Studies in hydrocolloid-based food inks have even identified approximate rheological printability windows in which printable pastes exhibit characteristic phase angle and relaxation behavior associated with self-support after deposition. This reinforces an important concept in food printing. Food inks are not simply edible mixtures. They are rheologically engineered materials. That engineering begins with formulation design. Hydrocolloids such as xanthan gum, Carrageenan, pectin, gelatin, alginate, methylcellulose, guar gum, and agar are frequently used to modify viscosity, yield stress, and structural recovery. Proteins contribute network formation and thermal gelation. Starches provide bulk viscosity and post-heating reinforcement through gelatinization. Fats alter lubrication and mouthfeel while affecting phase structure. Water controls hydration, molecular mobility, and interactions between dispersed phases. These ingredients are not added simply for nutrition or flavor. They function as structural engineering components. The formulation must be designed not only to taste good, but to survive flow, deposition, and stabilization. And importantly, food printing does not rely on only one manufacturing mechanism. Different printing technologies shape food through different physical principles. Extrusion-based printing deposits continuous strands of viscous material through pneumatic piston-driven or screw-driven pressure systems. This method depends heavily on rheological control, nozzle flow behavior, and strand stacking stability. It is ideal for paste-like foods such as doughs, purees, gels, cheese-based systems, meat pastes, and protein-rich formulations. Inkjet printing operates on a very different principle. Instead of depositing continuous filaments, it ejects tiny low-viscosity droplets with high spatial precision. Because droplet formation depends on surface tension, viscosity, and wetting behavior, inkjet systems are more suitable for edible coatings, flavor deposition, nutrient patterning, printed colors, and localized functional compounds rather than building thick self-supporting structures. Binder jetting uses yet another shaping mechanism. In this process, a liquid binder is selectively deposited onto a powder bed, causing local adhesion and solidification of particles. Powder flowability, particle size distribution, capillary penetration, and binder-particle interactions become the dominant engineering factors. This is fundamentally different from extrusion because structure emerges from selective consolidation of powders rather than filament stacking. Selective sintering uses localized thermal energy to fuse particles, often in sugar-rich or powder-based systems, where melting and resolidification define geometry. Each technology uses a different physical shaping principle, and because the physics changes, the material requirements change too. A formulation optimized for extrusion may fail in inkjet printing. A powder suitable for binder jetting may not work in thermal sintering. A low-viscosity liquid that forms excellent droplets may collapse instantly in extrusion printing. So successful food printing is not simply about selecting a printer, it is about matching material physics to fabrication mechanism. But even a perfectly printed shape is often still unfinished. Printing creates geometry, post-processing creates stability. Many printed foods require baking, steaming, microwave heating, cooling, freezing, or controlled gelation after deposition. These steps induce molecular transitions that permanently stabilize the printed architecture. Starch granules gelatinize as heat disrupts crystalline regions and promotes water uptake. Proteins denature and form new intermolecular networks. Hydrocolloids undergo thermal or ionic gelation. Fats melt, redistribute, and recrystallize. Water migrates between phases, altering texture and structural cohesion. These are molecular transformations, but they determine whether the printed food survives as a real edible product. A printed structure that appears stable before baking may collapse during heating if water migration becomes excessive. A protein-rich ink may harden too aggressively if thermal denaturation creates an overly dense network. Surface dehydration may improve crispness but create fracture. Thermal history becomes part of the engineering process. In this sense, printing does not end when deposition stops. It continues through structural fixation at the molecular level, and this leads to perhaps the most important engineering insight of all. The final quality of a printed food product is not determined by shape alone. It emerges from interaction. Formulation determines rheology. Rheology affects deposition. Deposition influences geometry. Geometry changes heat transfer and moisture migration. Thermal processing alters molecular structure. And together, these interactions determine texture, mouthfeel, structural integrity, moisture retention, nutrient localization, and sensory quality. This is why three-dimensional food printing is best understood not as a novelty machine that makes interesting shapes, but as a convergence of digital manufacturing, rheology, material science, transport phenomena, and food engineering. The machine may deposit the layers, but the science behind those layers determines whether digital design becomes real food.